It looks like people are slowly joining.
All right. Hi, everyone. Welcome to our webinar. This is the first in a series of 3 for the Western Region CCAs. My name is Eryn Wingate, and I will be hosting today. We're just going to wait for a few more people to come on in. We give it a couple minutes, and we'll talk about the agenda and get started. It looks like we have a few more people still coming in. So for those of you who just joined, welcome. I'm glad you could make it to today's webinar. My name is Eryn Wingate, and I'll be hosting and announcing our speakers for today. So we're just gonna wait a couple more minutes here as people filter on in. All right. Well, I think we still have people coming in, but I'll go ahead and start the webinar. I'm Eryn Wingate. If you've just come into our conference here, this is the Western Region CCA's first webinar in a series of 3 that we're going to be doing every other Friday. So I'm excited to start us off, and we've got a really good lineup scheduled for today. We're going to spend the first hour talking about salinity management and soils, and then we've got a talk on vineyards, and we'll finish up with avocados. So I think that there's going to be a lot of interesting technical and practical content for today, and you'll get your CEUs as well. So make sure that you stay until the end. We'll be putting the the QR code, couldn't think of the word, up on the screen at the very end. So make sure that you stay and you scan that in your app, the Certified Crop Advisor app. And as a backup, if you don't, if you've logged into this webinar, we'll have a record of that we can email to the ICCA. So if you've got questions during this, please type them into the chat. We'll leave questions for the end of everybody's talks. So yeah, I think we're ready to get started. And first up, we've got Jerome Pier. He works with QualiTech Lab, and he was also the former chair of the Western Region CCAs. He is going to give a presentation on managing crops under saline conditions. So he's going to go over the soil chemistry in saline or sodic soils, how that affects different crops and what you can do about it. So Jerome, whenever you're ready, take it away.
Okay, thank you very much.
Thank you.
Okay, I'm Jerome Pier, and I'm glad to be with you today. This is a presentation on managing crops under saline conditions. I just want to let, is everyone seeing my presentation? Are we good? All right.
No, it's not live yet.
No? Okay.
There you go.
Oh, I need to share it.
Yeah, hit the share screen button.
Thank you. And we want this one. There we go. How is it now?
That's great. Thank you.
Thank you. All right, let's roll. All right, thanks everyone for being here. I'm Jerome Pier, past chair of the CCA program, and I'll be talking about managing crops under saline conditions, saline and sodic. So definitely want to try to distinguish those. If you get anything out of this, is what is the difference between those two terms? So the most important thing is that this quote, I think I love this quote from Cadillac Desert. If you haven't read it, it's a great book. But this comes from the USDA Riverside. Jan van Schilfgaard said that salinity is the monkey on irrigation's back. And since we are irrigated agriculture all through and through, you know, this is definitely a problem for us out here in the West, where we pretty much irrigate everything we do. So the whole idea here is when you apply irrigation water, if you don't have good drainage or it drains too slowly, this is a quote from Jan, then salt builds up in the root zones, damaging the structure of the soil and ruining it forever. And that there have been civilizations that have their agriculture was destroyed by salinity problems. So the good news is that Jan said you can tune your crop mix and irrigation practices essentially and keep that problem at bay. So what I'm going to talk about for the next hour is, first of all, covering this whole confusing topic between sodic and what is sodic versus saline conditions. And then we'll talk about mostly about sodic problems and how they relate to infiltration. And then we'll get into salinity problems and talk about crop tolerances and what we can do about the saline conditions. And then we'll wrap it up. So the most important thing is that people seem to get confused over what is saline, what is sodic, what is salty. I think a lot of that has to do with people talking about table salt being sodium chloride, you know, and sometimes when you say I have a salt problem, I have to ask, do you have a saline problem or do you have a sodic problem? Do you have a problem with sodium or do you have a problem with total salt? So let's do some definitions and make sure we're clear on this. I'm going to define saline soils first, and saline soil is something that has an electrical conductivity. When you do a saturated paste extract, take the solution out of that saturated paste, and you put a conductivity meter in it, if the conductivity of that is greater than 4 decisiemens per meter, then you have a saline condition. And that's just the standard soil science definition for a saline soil. And then what that means is that soil is high in total salts. So it could be sulfate, nitrate, calcium, magnesium, everything that's in that soil solution that is not water is a salt in the form of ions. And so that high salinity has a big impact on plant yield. Plants have to expend a lot more energy in order to extract the water from that saline soil solution. And what's interesting, and we'll talk about this later in the presentation, but plants have different tolerances to different levels of salinity. So you can use crop mix as a way to get around saline problems and to clean up different saline type of conditions. So we talked about saline soils first. What is different is sodic soils. So a sodic soil is specifically talking about sodium, and it all has to do with the percentage of sodium on the cation exchange complex. So how cation exchange being all the negative charges in your soil particles, and so all the positive charges attached to those negative charges. And so if sodium is starting to dominate there, or there's a higher percentage of sodium compared to magnesium, calcium, potassium, and other cations, then you are running into a sodic soil. And the specific definition is sodic soil is when you have what's called an exchangeable sodium percentage of greater than 15%. And we define that exchangeable sodium percentage as exchangeable sodium divided by the cation exchange capacity in terms of milliequivalents per liter times 100. So when you have more than 15% sodium on the cation exchange, then you definitely have a sodic soil and you're going to have some serious problems. And it's not uncommon here in California to have these issues out in the Western US, actually. You can also have structural problems even when the ESP or exchangeable sodium percentage is above 6% sodium on the exchange complex. So, greater than 5 is pretty bad. And when we get above 15, we've got some serious problems. So ESP is typically a soil measurement. When we're looking at sodium issues, the first thing I want to do is I want to see a water quality assessment as well. And typically on a water quality analysis, you'll see this sodium absorption ratio. It's a water quality thing. You can see it on a soil test as well. But, basically, this is just a ratio in terms of milliequivalents per liter of sodium being the bad guy, and the good cations being calcium and magnesium in your water or in the soil solution extract. That sodium absorption ratio is just basically taking the concentration of sodium over the average concentration of calcium magnesium. And we take the square root because calcium magnesium have 2 positive charges, sodium has 1. But, so it's a unitless number, the sodium absorption ratio. And we have some information that tells us when sodium is out of control here. So basically how sodium affects soils is that sodium, it's very interesting. Sodium has a very strong positive charge. So what happens, it has a very dense nucleus and it has that single positive charge, but it attracts a big shell of water around it. And so it actually dilutes the positive charge down so much that it is weakly held to the clay layer. And so you have a very thick envelope of water when that sodium is loosely held onto that clay layer. Whereas calcium has a much larger atomic radius. It has 2 positive charges. There's positive charges there that calcium can use to attach to a clay particle, which is negatively charged. And so, basically the calcium is something that will allow clay particles to be attracted together, bonded together by the calcium, whereas sodium, the big sphere of water around the sodium atoms repels those clay layers. And let's look at another way of looking at that. So what happens is you have clays that have these flat layers in them. And if sodium gets in there between those layers, it will swell those clay layers apart, and it will squeeze your pore space down to the point where water can no longer penetrate. You can't have air leaving the soil. You can't have water going into the soil, and the water will just puddle. And so that's why sodium affected soils and high sodium waters tend to have a big impact on water infiltration into the soil. So that's kind of a little bit of the chemistry on why sodium is such a problem. Really the high sodium concentrations result in reduced permeability. So the movement of the water through the soil or into the soil, but also because of the effect of sodium on the clay molecules or the clay layers, you can have an effect on tilth, or basically you can disperse those clays to the point where you no longer have good soil structure, and the soils can become what they call massive, where you have a real hard time getting any sort of air into that soil. Water, air movement all gets restricted when sodium levels are too high in that soil. So calcium is your best friend when it comes to fixing a sodium soil, because calcium can displace that sodium. Calcium tightly held to the clays, sodium weakly held, and calcium can basically turn things around. So another thing to consider, and while we're on the topic of poor infiltration, it's important to know that water that is very pure has what we call a snowmelt water. So the Bryant Kern water on the east side of the San Joaquin Valley, water that really hasn't had a lot of time to gain salts in canals, things like that. I mean, that east side surface water is very low in salts. And so it can have problems with permeability as well, just like high sodium water, because there's no calcium in that water to help flock those clays and help keep those pores open and allow water to percolate. So just like high sodic soils or high sodic water, pure water can cause problems with infiltration as well. But what is really a challenge is if you have water that's very low in calcium, so it has a high sodium adsorption ratio, or SAR, but then it also is very low in total salts as well. So water low in total salts, or that snowmelt water, has a very high surface tension, and so it's very challenging to get that water to go in the ground. And when you have a combination of those factors, so water with low salinity, but also high sodium in proportion to calcium magnesium, then you really run into severe infiltration risks. And you can see that where the sodium absorption ratio is high and the electrical conductivity is low, then we have the most severe cases of infiltration problems that you'll run into. So you can see it kind of runs backwards. From green is good in terms of infiltration, and the electrical conductivity of that water. Red is bad, severe infiltration problems. You see the salinity levels, or EC, of your irrigation water is low. That's where things are the worst. So the sodium absorption ratio, usually if we have a SAR that's greater than 3, we start to begin to worry about our irrigation water infiltration. And then once we get above 6, then we're really looking at some severe problems, and we're going to have to definitely do something. Otherwise, the water will just pond up and it will never get into the ground. So, and that causes lots of problems with aeration. Roots need air. You need to get the water to move through the surface and into the soil, leach salts, things like that. So infiltration is very important, and too much sodium can cause real problems. So a small amount of sodium in very pure water can cause big problems, but the trick is to use calcium. Gypsum is one of the most common amendments for fixing a high sodium or sodic soil. Calcium thiosulfate, calcium chloride, there's things you can use, soluble sources of calcium, to help fix a sodium dominated soil. So that's a sodic condition. Sodium is the one thing that we deal with in our irrigation water and in our soils that the plant doesn't really need, and it causes big problems with infiltration, causes big problems with soil structure. Let's talk about salinity now, or just total salt problems. So why do we have salinity problems? And basically just when you have water moving through rivers or underground ancient marine beds that have been buried, over like 1,000 feet down on the west side of the San Joaquin Valley, you've got these total salts. It can be calcium, magnesium, bicarbonates, any sort of ions in there. They just tend to accumulate, and especially in our surface water, If it sits in our reservoirs for too long, you'll have evaporation, the water leaves, but leaves those ions behind, and it just increases the salinity of that water. If you ever look at water analysis of surface water, usually in the early spring, it has its very best quality. It's usually fairly pure, but as the time goes on, or during the drought that we're having now, you see that surface water quality gets pretty salty. So all the salts that are in there tend to build up over time through evaporation in our reservoirs. So soils become saline as we continue to add more of this high salt irrigation water. And if we have problems with leaching, so we can't move those salts past the root zone, and we start to build those salts up in the root zone, just like that first slide that Jan van Schildgaard was saying. Basically those salts will have a big impact on our crop yield and can affect soil physical properties as well. But how salinity, total salinity affects crop yield is the fact that there's this osmotic potential difference. When plants need that water, if there's less water and more salt, plants have to exert an extra amount of energy to get that water from a salty soil than from a salt-free soil. And that just has to do with that osmotic gradient between saline soil and less saline soil. So if as that plant is expending this energy to deal with these excess salts, they have to expel the salts when they take them up so that the plant doesn't die. All that extra energy that the plant is getting from photosynthesis can't be used for crop growth and development or yield, and we see reductions in yield under saline conditions. Also, in general, I'm not going to talk about it today, but some ions can also be toxic, and that would be sodium, which affects our soil properties and water infiltration, but also chloride can be toxic. We know boron can be toxic as well at certain levels. I mean, chloride and boron are essential nutrients, but in too high amount, they can cause real problems with toxicity. But let's get back to salinity and crop yield. And there's a very specific relationship that talks about what the effect of salinity is on crop yield. So this equation where we have the relative yield, or basically that's the yield that you would get with all things being equal. So the same management practices, but all we're changing is the amount of salinity in our irrigation water or in our soil. That yield changes due to the effects of increasing salinity. So when we have no saline conditions or a non-saline condition, our yield is 100%. So it's a relative index kind of a thing. As we look at our soil salinity, so that would be the EC of our or electrical conductivity of soil saturation extract, put that in the equation. And then plants have these specific thresholds. The threshold salinity, basically salinity has no effect on yield whatsoever up to a certain level. And then once we hit that number, or whatever A is, that threshold salinity in terms of EC, once we go above that, then we start to see a linear decrease in yield. And that is that rate of decrease is predicted by the slope B in that equation. And so that's a little hard to imagine until you see what it looks like on the graph. So on this graph, we have relative crop yield on the y-axis. We have increasing salinity of our saturated paste extract on the bottom, on the x-axis. And we have different crop groupings. We like to think of them as either sensitive to salinity, and so those have a very low threshold before you start to see an effect of salinity on crop yield. So in the sensitive class, if we get up to about 1 decisiemens per meter, then beyond that, sensitive crops will start to lose yield. And those B values, the slope, the bigger that B value is, the more steeply that slope affects the crop yield. So you get to the point where, with a sensitive crop, if you are up around 5, you're probably about 40% of your relative crop yield, just based on salinity alone. And then we have some crops that are very tolerant on the other end. where something like date palms, I'll show you in just a little bit some examples of various crops, but something that's tolerant can handle a great deal of salinity. It's not quite seawater, but no effect on yield whatsoever, even at an EC of 10. Maybe you're aware pistachios are quite salt tolerant, and so they can handle easily EC of 8. And then even once you get beyond that, tolerant crops can handle quite a bit of salt before you start to lose significant yield. So you can see the slope of those tolerant crops is much lower than what we have with sensitive crops. So here's some examples of those different crop categories. As I mentioned, date palms are on there. You can grow date palms up to a pretty high level. They're basically these thresholds. Cotton can handle up to 7 EC before you start to see problems. Sugar beets, Bermuda grass, asparagus are fairly tolerant of salinity. Moderately sensitive crops, you're looking at a lot of our vegetable crops, and then alfalfa actually is moderately sensitive. Lettuce, sweet corn, potatoes, cabbage, things like that can handle a bit of salinity, but then you start to see that as the salinity increases beyond the threshold, that there's a pretty rapid drop off in the relative yield. And then we get into the sensitive crops. So a lot of our perennial crops, and also onions, strawberries, things like that, the citrus, those are quite sensitive to lots of salt. And so, the strawberries, carrots, things like that, and basically, they can't really take much salt, and you need to really manage your salinity quite well in order to not lose yield based on salts alone. So some examples would be onions. Each crop has its own set of thresholds and its own particular slope, as I mentioned in that first equation. So onions, sensitive crop, basically can only handle up to about 1 or 1.2, something like that. And then the yield will drop off pretty quickly. Whereas we go out to dates, you start at about 4, and then they can go all the way out to basically up to 20 EC before you start to see any issues. And so, and wheat is somewhere in between, moderately tolerant, barley much more tolerant than wheat. So lettuce is somewhere in between. So these would be examples of 4 different crops, but you saw the tables that I had listed before. And I've got some references at the end of the presentation that shows you where to find all these tables that were generated by a professor down at UC Riverside back in the 60s. So now we've talked about saline conditions, sodic conditions. What do we do about it? How do we manage that? Since these are common situations we deal with all the time, some of the biggest questions I get from PCAs and CCAs in the field is, what do I do about this water test, this soil test, where we have a salting condition? So basically, what you need to do first is get soil and water tests. Basically get good samples of your soil, of your water. And for sodic soils, as I mentioned earlier, we can reclaim sodic soils with calcium sources. Gypsum is typically the least expensive way to go. For just a bulk amendment, it's an excellent way to apply a lot of calcium to displace that sodium and get it out of there. Sulfur, elemental sulfur can also be used, or sulfuric acid. I'll talk about how that works in just a bit, but you do need free lime or free calcium carbonate in your soil to be able to make sulfur work, because what we're looking for is calcium ion to be able to displace the sodium. Leaching fraction is what we're going to use to manage our saline irrigation water. We need to, ironically, if we have salty water, we need to apply more water to keep the salts moving beyond the root zone. So assuming you have good drainage, we can just apply extra water, and that will help us manage that saline condition. We can blend different irrigation sources together. If we have fairly clean surface water, we can blend it with saltier water and then get it to our crop tolerance level. or sometimes acid treating irrigation water can make a difference by removing bicarbonates. I'll talk about all these things in the next few slides. Bed shape can have a big impact on how we manage that salinity, as that salt wicks through our beds and ends up, on the sides or in the middles, depending on how we shape our beds. Seabed shape can have a big impact on early establishment. And then irrigation methods, we're doing a lot more with drip now. How you manage your sprinkler irrigation can have a big impact on managing these saline and sodic type conditions. So sodic soils, typically from a soil test, we'll be looking at, you'll get a number of terms of mill equivalents of sodium per 100 grams of soil. And then you can back calculate, how much calcium you need to change that equation. ESP below, say 10% would be great. Sometimes it's not economically possible to put enough gypsum on, and it's sort of a long-term project. But calcium is your friend in this case. And so for every mill equivalent of sodium you need to remove, you need about 1.7 tons of gypsum for every acre foot of soil that you're trying to reclaim. And you're going to need some pretty decent quality water if you're going to reclaim these sodic soils. You're also going to need good drainage. I mean, the sodium has to have some place to go. Now, if you do have free lime in your soil, you can use elemental sulfur, and that elemental sulfur will turn into sulfuric acid. I'll talk about this in a second. Create free calcium, and then so basically about 1/3 of a ton of sulfur will reclaim an acre foot of soil if all you have is 1 mill equivalent of sodium that you need to get rid of. But the important thing to understand is not all gypsum is 100% pure. These numbers for the gypsum, the 1.7 is based on 100% gypsum. Most gypsum is, in that 60 to 80% pure range. So definitely get an analysis from your gyp supplier, and have a look at the quality of the gypsum as well. Most of the sources coming out of Nevada are pretty good quality. So, but they're not all pure gypsum. So you will have to add more than what this 1.7 tons is implying. So I did mention the fact that elemental sulfur can be used to reclaim a sodic soil, but what you have to do is make sure you have free lime or calcium carbonate in the soil. On some soil tests will list that as a fizz, which is a qualitative measurement of calcium carbonate. They just drop some dilute acid on this surface of the soil and watch it bubble. And if it bubbles a lot, that you've got a lot of free lime. And if it doesn't bubble at all, you don't have any free lime. So if you don't have free lime, then sulfur it can't help you. But basically, elemental sulfur applied to the soil that contains free lime will be through Biobacillus bacteria that are present in almost all soils. If you have well moistened soil and good oxygenated soil, aerated soil, the Biobacillus we use that elemental sulfur as a food source and convert it into sulfuric acid in the soil. That will react with your calcium carbonate and give you free calcium. So you get a twofold reaction with elemental sulfur. If you have a lot of free lime, you typically have a soil pH that's above 7.5. And so, typically you want to lower your soil pH and provide free calcium. And you'll get both of those effects with elemental sulfur. And it's fairly economical to do that. Now, if we have irrigation water that has a deal of salinity to it, or our soil is pretty salty, basically, especially with saline irrigation water, what we need to do is apply more water. And this equation, this leaching requirement, or leaching fraction, sometimes it's called, is a way to calculate the amount of extra water that we need to apply to keep those salts moving through the profile and make sure that the salts don't build up in the root zone, as we talked about in the very beginning of the presentation. So in order to use the leaching requirement equation, you need to know what your water electrical conductivity is, so that ECW. And then from the crop tolerance tables that you can find online from the FAO publication I'll mention at the end of the presentation, And knowing what the evapotranspiration or water demand is from the crop, we can figure out how much water we apply to apply that extra water and leach salts past the root zone. So in this case, that ECW is the irrigation water electrical connectivity. ECE is coming from a table. So basically just in the numerator, we have electrical connectivity of the water. In the denominator, we have 5 times the electrical connectivity of what the crop tolerance is going to be. And then we subtract off the electrical connectivity of the water again, and that gives us the fraction. And then if we know what our water demand is per day, we just take that divided by 1 minus the leaching fraction. That tells us how much extra water to put on. So in this example, let's say we have lettuce, and lettuce to maintain that salinity threshold of 1.7. Basically we don't really want to lose any yield. So assuming we're right at that A value that we have in that salinity tolerance equation, we have electrical connectivity of the water of about 1.38. So it's not too bad. That's about pretty typical for waters around here, would be reasonable. And if that lettuce is taking up 0.2 inches per day, the leaching fraction, we need about 0.2 more water, or a fifth more water than what we would normally put on based on that equation. And so the 0.2 of an inch per day looks like we bump that up to 1/4 inch just to make sure that we're applying extra water so the salts don't build up in the root zone. So that's how you look at leaching requirement. So more water is better when we have saline type conditions. Also, you can blend water, and it's a simple equation here. If we have 2 different water sources, hopefully one of them is better than the other one. You can figure out how much to blend of each different source based on this equation, when the electrical connectivity of the blended water is equal to the first source times A and the second source times B added together. And basically the relationship would be, A plus B equals 100, or 1 in this case. So an example, we have the water that from the previous example has an EC of 1.38. The second water has like more than double the EC. So that's a pretty tough water. How much of that rough, let's call that a saline well water, can we use for this lettuce crop that we don't want to go above 1.7? Otherwise, we'll see a yield decrease. So basically through that equation, it looks like if we blend in 14% of that saline water with 86% of that cleaner, let's assume it's a surface water, we can maintain that electrical connectivity that will prevent that lettuce from seeing a yield loss. So fairly simple equation to get it that time. Bicarbonate in your irrigation water, and carbonates too. Usually if you combine bicarbonates and carbonates together, the lab will call that alkalinity. So those 2 ions, those can tie up calcium. Basically, they react with free calcium in your irrigation water, especially as that water sits on the surface and tends to evaporate. You'll form calcium carbonate, which is an insoluble mineral, calcite or limestone. And so bicarbonates can cause real problems with our irrigation water quality. So sometimes you can remove, acid treating irrigation water is about the only way you can get rid of any sort of ions by reacting the bicarbonate with an acid and releasing carbon dioxide. So basically, the way to do this, if we see we have a bicarbonate level in our irrigation water that's above 3 milliequivalents per liter, or I would say that's about 180 part per million bicarbonate from a water test, then you would ask your lab, if you get those results back, you want to get back to the lab and say, if you still have my water sample, could you run a buffer curve with sulfuric acid and tell me how much I need to do add of sulfuric acid in order to get the water pH down to about 6. And that will remove about 50% of your bicarbonate. If you get the water pH down about 4.5, that'll remove about 90% of the bicarbonate. But typically we go shoot for a target of about pH of 6. And that will get a bicarbonate level of 3 down to about 1.5, and then you shouldn't really have any problems with bicarbonate. Sulfuric is really the cheapest way to go if you have a great deal of bicarbonate in your water. But the only problem with sulfuric acid is, I hope you understand how dangerous it is, and you really only want to go through a professional dealership. There's Elite, there's Vertical Brothers. There's a bunch of companies out there that will come and set up a turnkey sulfuric acid injection system for you. You really shouldn't be handling it yourself. Ampuric is a product, or US 1549 would be a product out there. Urea sulfuric acid, which is a safe product, so it'll tear up your genes, but it won't damage your skin. But sulfuric is extremely dangerous. But ampuric can be used for moderate bicarbonate. So anything that's kind of in that 2 to 3 mil equivalent bicarbonate range, you can treat with ampuric, and that'll make a big difference. Maybe just periodic treatment with ampuric will help clean up some of that stuff. I did mention seed bed shaping, and so we don't do a lot of furrow irrigation anymore, but you can see that if you have saline type situations, and you're irrigating with every single row with your furrow irrigation, so water running saline water, your salts are going to tend to build up right in the center of that bed. So, you probably want to plant more on the shoulders if you're irrigating every single row, and let the salts build up in the middle. Whereas what you can do is alternate your irrigation every other row, but you always want to run the water down the same row. You don't want to be pushing the salts back and forth. So alternate row irrigation, just keep irrigating the same row, and you'll keep, you want to plant on the outside of that seed bed, away from, closer to the water and away from where the salt will build up on the edge of the bed. We're doing a lot more with drip irrigation now. So buried drip is actually a pretty good way of handling saline type conditions. You're irrigating more frequently, keeping that soil moist so it doesn't dry out. There's more water in there, flushing salts below the root zone, but your salts will tend to build up on the edges. So if you have the drip buried too deep, you have to watch out that you won't build up a salt zone right in the middle of that seed row, right in the middle of the bed. So surface drip will push the salt to the outsides and down. So surface drip is a little bit more easy to manage. Just be careful with the buried drip. You can cause real problems as that water wicks up to the surface and carries salts with it. Make sure you precondition the soil with your buried drip. And in general, sprinkler is probably your best way to go for initial seed germination, since the water is coming from the top down, pushing salts below the seed line. And so frequent light irrigations are going to do a pretty good job keeping those beds moist and leaching salts below the seed line. But watch out if you have saline water and you're sprinkling. You don't want to do it on hot, dry, windy conditions, because the salts in that saline irrigation water can definitely burn leaves. And a lot of that is due to if you have high sodium and high chloride, those things will cause a specific ion toxicity. You'll get some scorching, some phytotoxicity with those ions as they evaporate on the surface of the leaves. So be careful with sprinkler irrigation. Great for once you're getting your seeds up. But once they're out of the ground, you probably want to switch over to drip at that point. So drip is really good for saline water. You're maintaining a high water content in the root zone. Basically the more water that you have in there and the less salt, just continually or frequently applying irrigation water and keeping the bed moist is going to help those plants not have to work so hard to get the water out of that saline type condition. And it also does a better job of leaching salts out of the root zone. But you have to be careful with your drip emitter spacings. Make sure that the drippers are close enough together so that the water is moving laterally, and where those wetted zones will merge and push the salt levels down, so below the root zone. You definitely want to be careful with drip for germination. Like in onion type situations, they'll typically start them with sprinklers and then switch over to drip once the onions are out of the ground. So you want to be careful with drip. If it rains, I mean, that would be great if it did rain. Rainfall can be your friend, but also rainfall, as we can see, the salts can build up on the surface with drip irrigation, and rain can actually wash the salts right into the root zone. So sometimes they recommend turning your irrigation system on if you have a saline condition built up on the edge of your beds. Turn your drip system on and flush those salts out. And you definitely want to kind of get some flushing, hopefully get some rainfall to flush salts out under drip irrigation to start fresh every season. So I think I'm coming to the end of my talk. This is a picture of the Dead Sea in Israel, where you can basically float in the saline condition of the Dead Sea is so much you can lie there and read the newspaper. So it's pretty saline. So in conclusion, excess salts are going to have a problem on your crop yield, but different crops can manage salts differently. So your crop mix is a good way to deal with salinity issues, growing pistachios versus almonds. Almonds being more salt tolerant, sensitive than pistachios can handle a great deal of salt. And then sodium is a specific problem in salinity management that has a big effect on our soil physical properties. You can get some toxic effects of sodium, but usually what happens first before you see plant toxicity from sodium is that you've had a big impact on your soil physical properties before you get a sodium toxicity. And really knowing the water quality and soil properties, so getting tests done before you go out and make your choices of which crop you're going to grow, are going to allow you to be able to manage these conditions better and allow you to farm these more questionable waters and soils. So salinity can be controlled by leaching those salts. You need really good drainage. You can add chemical amendments to your soil and water, gypsum, acids, sulfur, choosing the right crops and the right seedbed geometry, very important. And then choosing the right irrigation methods will help you manage to keep the salts out of the root zone and allow your crops to grow even if you have fairly rough conditions. So I'll leave this up for just a second here. Probably the most important book, and it's not even a book anymore. You can find this online at FAO.org. So just search in your Google toolbar or whatever search engine you like to use for water quality for agriculture, this FAO Irrigation and Drainage Paper 29 by Ayers and Westcott. Back in 1985, this is an excellent text that will help you with all the tables that you need to know for finding your salinity tolerances for various crops. And then there's another FAO irrigation and drainage paper out there that's a little more recent, 1992, not very recent, but I mean, salinity hasn't really changed over time. So these things are out there to help you. And with that, I will stop sharing and see if there's any questions. There's one from Daniel Robledo. I see a question that says, how tolerant are grapevines to salt? I think, Daniel, you probably know better than anyone that a lot of salinity tolerance is based on the rootstock that you're choosing for your particular grapevines. I think we're going to get a good talk on grapevine nutrition management. Maybe Paul can talk about that a little bit. But, a lot of, you can do a lot with choosing the right rootstock. And so, I would say grapes are moderately tolerant to salinity, but it really depends on the rootstock sign combination. Be my quick answer there. Any more questions? You're welcome, Daniel. Good to hear from you. Okay. Anybody else? I know that was quick and dirty. There's a lot more to this, but
thank you.
You're welcome.
Well, if if nobody else has any questions, I'll jump in with one. So if we've got a saline irrigation water, but a lot of the salinity might be coming from sulfate, and if we've got sulfur buildup in the soil, is sulfate less toxic than some of the other salts? Should we be worried about sulfuric acid injection? Are
That's
there
a
other
great
options?
question. And I also saw somebody in the question, there is a question about sulfuric acid on soil organic matter. So that, I think you should be a little bit concerned about sulfate. It's not, I've never really seen it get toxic until it gets to extremely high levels. But the effect of sulfate is you're going to have your biggest effect on the electrical conductivity. So it's not going to really affect your soil properties as much as it will affect the salinity of your irrigation water or your soil. And I believe that also, if we do build up too much sulfate, there could be issues. You know, we talk about cation interference, you know, magnesium and potassium can compete. You can get competitive interference at the root zone, at the root level for uptake. And I think if we get too high with our sulfate, you can have competitive interference with other anions. So phosphate, I believe, can be competitive with sulfate. So I think we do have to pay attention to the sulfur levels, but sulfur is a really weird one, Eryn. You know, I have seen high levels of sulfate in the soil and actually seen sulfur deficiency in tissue tests, and the opposite. You know, I've seen deficient levels of sulfur in the soil and then have it be adequate in tissue tests. So sulfur is a very strange one, but I would say salinity is where you're going to see the biggest impacts of excess sulfate. And then this question about sulfuric acid on soil organic matter, that is a really good question. Typically, when we're applying sulfuric acid, we're only applying enough to reduce our bicarbonate level in the irrigation water by half, by reducing the pH of our irrigation water to about 6. And so typically 6 is in that sweet spot for most of our soil conditions. You know, I don't think you're really going to have too much trouble with acidification if we're only just knocking out the bicarbonate in irrigation water. If you crank that sulfuric acid injector up more and you're lowering your pH even more, then I think you might see some impacts. But I've actually seen some benefit to increasing the sulfuric acid level when we have soils that have very high free lime. You can actually make an impact on crop productivity. But in terms of what it's going to do to the soil organic matter, there's this one question from Barris. You know, that's a good question. I'm not really sure what the impact of sulfuric would be on soil organic matter, but typically it's not going to be that concentrated in terms of our injection rate. So I think soils have pretty good buffering capacity, and it shouldn't have too big an impact on soil organic matter. Maybe someone else on the panel can answer that question. Anyone else? All right. Oh, well, here's another one. Rogel Rogers. Do you think growers can benefit from an on-farm recharge as a means to dilute salinity levels in the root zone during the dormant season on crop like almonds? So I think, yeah, so off-season recharge, I think, is definitely recharging the aquifers, flushing. The only thing, Rogel, I would say about that is be extremely cautious when doing this on-farm recharge in the winter with the amount of nitrate levels that are left in your soil. You definitely want to have your growers get their nitrate in the soil as low as possible. Below 10 parts per million in the saturated paste extract would be a really good number to get to, because, you know, our drinking water standard is around 10. So if we can get our nitrate levels as low as possible, then winter is a really good time to apply a ponding type situation. Once our permanent crops are dormant, then yeah, I think we could do some good leaching there. You know, if we get enough rainfall, it would be great. But if we have some clean surface water, you know, really low salt surface water and we can pond our permanent crops and let that water move to the aquifer and get some recharge, I think that is a good way to go. But we don't want to cause nitrate pollution. So make sure that your nitrogen levels have gotten lower. And one more, and then I'm going to quit. There's some period where moderate soil salinity suggests to have more flowers. Ooh, interesting. So, I think I think you can manage stress. That's an interesting idea. Can we use soil salinity to manage the stress in our crops to try to modify certain quality characteristics? I think in wine grapes, that's probably a wine grape type question. But I've never heard of anyone doing that. But usually water management is the best way to go. But I think if the crop is under a mild stress, you don't want to go too crazy. But I think mild stress could have an impact on sugar accumulation. But if you overdo it, I mean, you can end up damaging the crop as well. So it's not anything I'm familiar with, but maybe Paul can answer that question during his presentation. But that is an interesting one. Usually water management is the best way to go, slowly tapering off your water applications to manage the root zone. And a mild water stress is going to be very helpful for getting your bricks up. But maybe a little bit of salinity could do that too. But that's a very interesting question.
Awesome. Thank you.
All right, I'm going to stop right there. And I think Miranda's going to provide my email. If you guys want to send questions after the fact, hit up my email and I'll be more than happy.
Yes. So everybody, if you came into the webinar a little bit later, stay until the end. That's when we'll have the QR codes posted so that you can scan it and get your CEUs. And we'll also show all of the speakers' contact information if you'd like to send them a question later. All right. Thank you so much, Jerome. It was great. And so our next speaker is Paul Crout, and he works for Helena. He's the senior agronomist there and product manager. And he's also the certified crop advisor of the year for the Western region. So we're very happy to have him here. Paul has taught me so much. He's both a CCA and a PCA, very well-rounded in fertilizer, irrigation, and pest management. So he's going to talk today about developing nutrient management plans for wine grapes. And I think that just about does it. Are you ready to go, Paul?
I am indeed. Here, let me share my presentation here, and we will get going. Yeah, just to actually answer a couple of Jerome's questions that were asked. I'm talking about using soil salinity to stress vines. It's having been a vineyard manager myself, there's too much disuniformity in the soil in order for us to rely on that. You might be able to have one section be, but really what we're trying when we're farming for and we're trying to manage stress, like Jerome said, we use irrigation because that's uniform across blocks, and we can manage that much more precisely. So there's my answer. I'm usually trying to get salinity down as much as I can because I want to deal with, not deal with adverse interactions with, we're applying fertilizer or doing a lot of our other practices. We don't want to do that. And then also Daniel's question on grapevine tolerance. Yes, it is definitely rootstock dependent. And so it really depends on rootstocks as well as your irrigation practices. So one thing, Salt Creek is not salt tolerant, just so you know. That is something that some people think, but no, Salt Creek is not salt tolerant. Anyways, thank you, Eryn. Great to be able to be talking to you today. So I have a half an hour. Eryn told me I have a half an hour to talk about building a fertility program for wine grapes. And this presentation is usually part of a 3-hour training that I do for staff. So you'll have to, forgive my brevity, but I'm going to be covering pretty high, I think, from kind of a 30,000-foot level, but really talking about some specific processes and the processes by which I go through when I am developing a fertility program, specifically for wine grapes, but this can be certainly applied to any crop at the end of the day, because really what we're trying to do is build something that's going to accomplish a couple of goals. It's going to obviously follow the 4 R's. We're going to be putting the right product in the right place at the right time, in the right method, and so that's one key. The other key is that we're building out a fertility program that's going to be answer the questions or answer the challenges that the grower has. In wine grapes, it's really interesting because we don't typically, we're not farming the grape at the end of the day that we're harvesting is not the end product. It is the raw material that goes into the end product, which is wine. And so a lot of times we're farming for chemistry and a juice chemistry and a whole host of other things. And that's why I like wine grapes, is because wine grapes can be really responsive to fertility, both good and bad. You can really screw up a crop if you have a bad fertility program, or you can solve a lot of challenges, or a lot of quality challenges or quantity challenges that your growers might have. So let's get started talking about building an effective fertility program. And so when I think about building a fertility program, I have this mantra that I go by, that anytime I'm trying to do something, and it's called by design, well-defined, and clear to all. When as being an agronomist and a consultant and even a grower, when I'm putting together a program, any kind of program, I want to keep these things in front of mind. By design, what does that mean? It is a well thought out, professional format that we are presenting or that we are creating. That creates consistency year over year over year. I have fertility programs for growers that I've written for 15 years. I can go back and I almost use the same format that I've used years and years ago, because there's a level of consistency. And you don't want to just put it on the back of a Denny's napkin, because you never know. That's not exactly professional. Second piece, well defined. What is it? What is the program? What are we trying to accomplish? And that really gets us to the 4 R's. It's specific products and blends, specific timings and rates. Those are all spelled out in this fertility program. As far as timing, is it bud break? Is it at 12 inches of shoot growth? Is it at bloom, et cetera, et cetera? We want to be very specific about what we're doing. And then finally, and this I think is the most important, having been a vineyard manager myself, it's clear to all. Is your program, does it make sense to the grower? Do you understand it? And above all, does the applicator or the irrigator understand it? Because that is the biggest challenge. If you build a program and you have 5 different irrigation blocks and you have 5 different rates for fertilizer on 5 different irrigation blocks, I can guarantee you that the irrigator probably isn't going to be able to get 5 gallons per acre on this one, 8 gallons an acre on that one. So we have to be really very, very clear in how we kind of develop a program, and that's where a lot of times the biggest challenge is, because it has to be clear to everyone, so everyone is on board. Because a lot of times we can have I've gotten phone calls where I've delivered exactly the right amount of fertilizer for this ranch, and they call me and said, hey, can you bring another 500-gallon bubble? We're only halfway through. So those are the challenges that we don't want to have. I mean, I guess from a retail point of view, that's great, but really from an agronomic point of view, we want to make sure that we're getting those rates on at the correct time. So remember this: by design, well defined, clear to all. I think that's really, really critical. So when you're building a program, there's a whole host of things that we really want to be thinking about, and that we really want to be, these steps that we want to do. It's not really, okay, let's just throw out, nitrogen, some AAA or, NPK or, whatever. We have to understand all the different variables that go into it. And that's really, I think, a key when we're thinking about an effective program. I mean, you can build a program that's pretty basic, but really an effective program, and especially nowadays where, the cost of fertilizer is, skyrocketed. We're triple, quadruple where we were last year. This is really where things become very, very important. So we want to do a number of things. First off, understanding our current soil and water conditions. Jerome touched on this, sampling. These are critical. You have to understand where you're starting from before you can even start making a recommendation. Second is to understand, the amount of nutrient that you're going to be needing from, for that crop. And then third, you're going to need to understand some uptake curves, and crops don't take up nutrients linearly. Well, permanent crops, especially wine grapes. I'll be talking about wine grapes specifically, I guess. Wine grapes do not take up nutrients in a linear fashion. They have times of high, rapid uptake in demand, and then they have times of low uptake in demand. And we want to time our applications to, to reflect those uptake curves. Fourth, we really want to build this fertilizer budget to address those uptake curves with rates and timing. And when I talk about rates, I'm going to talk about a lot about, I'm thinking about units. I don't really, until the end of a program, I don't think about analysis. I'm not thinking about 1034.0. I'm not thinking about, 3200 or 0025. I'm thinking about units. The analysis that comes at the end. And so a lot of people get tied up on and focused on, well, I need a 1085. What does that mean? It's no, how many units do you need? So we're going to go through a little calculator I have to help you do that. We want to be able to select our fertilizer sources. And again, because of time, I'm not going to really get into the differences between nitrates and ammonium-based and urea-based fertilizers. They all have different uses and different timings and different benefits. Same thing with, polyphosphates versus orthophosphates. Again, there are times when we want to focus on using orthophosphates versus polys. I'll touch a little bit on it, but unfortunately we can't go into fertilizer chemistry as much as I would like to in this talk. Then we want to, once we've selected our fertilizers and our blends, we want to jar test, because everything I do is blends. I build, everything is a custom blend. First off, because vines don't, necessarily need just nitrogen at this specific time. They need nitrogen and calcium and a little bit of phosphate or potassium. And sometimes they might need phosphorus and potassium and no nitrogen. And so typically I definitely go with the blend test, the blend approach. And we always want to make sure that when we are creating blends that we jar test those to make sure that they can actually be delivered to the field and applied. Finally, you have hopefully a prescriptive program form, some sort of format that you have that you can keep for your own records. I'll show you an example of one that shows, how much nitrogen you've applied over the course of the year, phosphorus and potassium, and it allows for planning and finally monitoring and adjustment throughout the season. Because I think when we develop a plan this time, this time of the year in the winter time, and then we initiate that plan, we want to monitor that plan throughout the season because, farming is grape farming, wine grape farming. It's an outdoor sport. Things change with drought or more rain or temperatures, and a lot of things can affect nutrient uptake over the course of the season. So we want to monitor utilizing tissue samples and then making adjustments. So if we can follow those key pieces, those steps, it doesn't really take a lot of time, but just being very, being very intentional about that in your thoughts is really critical. So let's look at some information that we need to start with when we're building a program. And this is typically information that I like to get, we want to get from the grower. And so in wine grapes, typically I'd like to get some historical yield as well as their expected yield, what they're expecting and what their goals are. I also like to get their fertilizer history, especially to be able to correlate how much phosphate and potassium they've been applying over the years, and that can help me kind of correlate some other, other information. Second, we want to get current, and you can see there's a star there, soil, tissue, and water reports. I typically soil samples within 3 years for me, unless you've been doing a lot of soil amending. You're putting tons of gypsum on or tons of soil sulfur or doing things of that nature. Usually soil samples within the last 3 years can give us a really good foundation, because that's kind of telling you what's in the bank at the end of the day, to keep things simple. I like to have tissue samples, if available, from the prior season, again, to be able to see where some challenge areas might be, especially around micronutrients, as well as potassium availability in those tissues. And then finally, water samples. Depending on, we can get into water sampling, but I think Jerome did a great job talking about water sampling as it relates to salinity, because that's usually what I'm concerned about, in addition to nitrates. Over here on the coast where I live, we have some wells that have some rather high nitrates, 30, 40 parts per million nitrate in our ag wells. That we need to take into consideration when we're building a fertilizer budget. So having water as well, because typically water is, of course, the biggest input that you make in your crop over the course of the season. And so we want to know what we're dealing with there. And then finally, what are the growers' expectations on fertilizer costs? I think this is this was a little shocking this last year. I built some fertilizer programs that were, budgeted at $300 an acre, and at the end of the year, it was, $500 an acre, just because of what fertilizer costs were. And so it's important to have that expectation when you're building out a program, because we can do a lot of things with fertilizer, and different types of fertilizers and different blends. And so understanding that expectation on cost can also help drive kind of where you're going when you're building a fertility program. And then finally, we need to understand what the nutrient needs for the crop are. I really love the CDFA FREP website. Daniel Geisler does a great job in really putting together some, kind of combining all this literature out there on these, and we'll touch on that really quick. But you really need to have an understanding of kind of what the crop demand is, what the needs are, kind of in order to have any kind of background into what you're going to input. And so that's the key. When is that nutrient needed? And that's some understanding from that website will help you, as well as literature. I'm a big fan of Dr. Marcus Keller out of Washington State. He wrote the Physiology of Grapevines, probably in my opinion, the preeminent wine grape physiologist out there. He's got a great book. It's about 2.5 inches thick, but if you want to deep dive into wine grapes, physiology, nutrient partitioning, stuff like that, be my guest. I have my copy. It's very dog-eared. And then finally, plan on your method of understand your method of application. Do you have drip system? Is it dry farmed? Can you do foliar applications? What are your application methods? Typically in wine grapes, we're on drip, so that's something key to take to think about. But what's your water availability situation? Can you only irrigate 2 or 3 times a year? Those need to be taken into consideration with your fertilizer program. So I'm just going to provide a quick little example here on an example for wine grapes. So we have 5-year-old grapes, which are really coming into their kind of peak production. Our target yield is 4 tons an acre. These are coastal premium wine grapes, so 4 tons is about middle what I deal with. Central Valley certainly, depending on the variety, you're up in the 10, 12 tons an acre. But really for us, we deal in this 3 to 6 ton to 8 ton, depending on, well, if it's Grenache, we can get up that high. But we really want to be, our balance is around 4. We have drip irrigation. Our last used tissues in potassium and nitrogen were both low, and our fertilizer budget's $400 an acre. So what do we need to do from the beginning? Understanding what our soil and water conditions are. So we take a soil sample analysis. This is an example of a saturation extract soil sample. And so what we see, we've got a pH of 7.9. Yes, this is typical coastal high lime, high lime soils. This actually comes from just West Paso Robles. I think I'll put my little laser pointer on there. Also look, and Jerome did mention fizz test. So this says high. Whatever high means, we don't know what that means. There are soil tests that you can actually, that'll give you lime content. But I know I have a 7.9 pH. I've got high lime, so I'm dealing in a very high limestone calcareous situation. You look at our sodium as well. We've got 9.5 milliequivalent. Our SAR is 5. So we've got some some things to think about here for sure. Here's our extractable nutrients. Again, there's some things to look at. We have no nitrate. This is typical. 1 part per million nitrate, 2 parts per million phosphorus. So basically no phosphorus. If you look, potassium's very low, 113 parts per million, and then our micronutrients are low. This is probably textbook West Side Paso Robles, high lime soil. We're in a ocean influence area. So if you look at our CECs, cationic calcium, cation saturation, calcium is about 77, mags at 16, which actually is pretty good. But sodium at 5.5, that's definitely something to think about versus potassium. And then I have a set of guidelines that I've kind of put together. This is based off of, I'll throw the plug out for the Western Fertilizer Handbook. Latest issue just came out. Awesome. I think I have my copy from 25 years ago is it's still in the bookcase, but I've created this chart and I pulled it from basically the Western Fertilizer Handbook, which is again a phenomenal resource when you're looking at soil tests. And looking at general guidelines. So really to identify those kind of targets that we're looking for, in the soil. So a little summary of that soil report. We have a high pH situation. So that's going to mean that we have very low availability of micronutrients and phosphorus, because that phosphorus is going to be tied up, what little phosphorus was in there is going to be tied up with calcium in that high pH situation. We've got some salinity things to think about, specifically sodium. It's marginal, but I wouldn't say it's limiting in that situation. And then we have really low nutrient content. So nitrate, phosphorus, potassium, micronutrients, et cetera. So we're going to take all those things into consideration in the soils report. All right. So now that we've seen what we kind of have in the bank with the soil, we need to kind of figure out how, what we need, how many pounds of N, P, and K we're going to be shooting for as part of our fertility program, as part of our fertilizer addition program. So understanding nutrient removal and demand, here's that UC Davis FREP website. It's got all kinds of different crops on there, both trees, annuals. It's a great resource. If you've never really looked at it, I would highly recommend just kind of perusing through, because there's a tremendous amount of really good information there. So we would click on the grapevine little icon there. And then that brings up this, nice simple NPK, growth, growth summary here. And you can click on each one of these little pieces, and it will have a nice little drop-down menu of a summary of information, and then also a lot of references. So this is a great tool just to kind of understand, give you a basic idea on, what soil applied N, foliar applied N, foliar phosphorus, soil applied phosphorus, timings and rates and ideas of general removal information. So I've found on the coast, I typically see that when, from a removal standpoint, I base my nitrogen on expected yield, and the number that I found that seems to work best for me, at least, is 4 pounds of nitrogen per ton of grapes. That's a pretty, the literature says between 2 and 8, 9, 10. So I've found that 4 is pretty good because I'm pretty conservative when it comes to nitrogen applications. I typically write as we go. I write nitrogen, negative recommendations, just because nitrogen is one of those things that we really need to be careful of in wine grapes, because excess nitrogen can cause some issues in the juice. There's some flavonoids and molecules called pyrazines that can cause issues with excess nitrogen that creates a vegetative flavor, kind of that green bell pepper flavor. And so that's something that we want to manage. So I typically look to base my nitrogen on yield, on expected yield. So I take that from nitrogen removal. When I look at phosphorus, typically it's about 2 pounds per ton. And I have 2 choices. Do I just replace the amount of phosphate removed at harvest, or do I think about building soil phosphate? And so those are two things that I would be considering. Typically, when I do liquids, I'm only replacing. I'm doing what the immediate need is, and if I want to start building phosphate or phosphorus and potassium as well, then I look to dry opportunities, just because liquid is just too expensive to use to build. So if we look at phosphorus, do we want to maintain those levels, or do we want to work on building? Well, shoot, in this consideration, if the grower can afford it, with phosphate, background phosphate at 2 parts per million, and my target is 12 to 15 to 18, I might consider a long-term phosphorus building program as well, if it can be done. And this is just a something to consider. pH really drives phosphorus availability, and so if we have a very low fertility level, and looks like phosphorus is most available at about 6.5, where we were at about 8. So you can see even that small amount of phosphorus that's in our soils, the report, it's pretty much not available. So I'm going to want to think about potentially managing soil pH as well, because if I add additional phosphate to this soil with that 8 pH, that phosphate fertilizer is going to tie up. So we have to address and take that into consideration when we're making a soil building recommendation. Same thing with potassium. I'm kind of the opposite on nitrogen. I have found I like to see my potassium levels higher, especially in wine grapes. I'm not afraid of potassium. Some people are afraid of applications or higher applications of potassium in wine grapes, because there's a concern about the pH of the grape juice. You can affect some issues there. It's all about timing in my mind, and following the correct timing. I typically like to get all my potassium in prior to veraison. That way the vine has time to be able to take it up, translocate it, metabolize it, and actually make use of it. Potassium applications after veraison, I've seen very limited beneficial effects on bricks at the end of the day. So again, are we just replacing our potassium, or are we adjusting? Are we going to be adding more than we remove based on potassium levels? And again, looking at this soils report, I would probably consider that I would recommend making a potassium building program in the fall based on these soils, to try and bring these levels up to a level that we're not just kind of riding the ragged edge and just replacing what we're removing. So let's look at nitrogen. This is a little spreadsheet calculator that I built years ago, and it's pretty simple. I usually use it for nitrogen. So I have my nitrogen removal. So we typically remove 4 pounds of nitrogen per ton of grapes. I enter the estimated tons. It kicks out basically how much we're estimated for removal. And then I have soil nitrogen credits, water nitrogen credits. So I take our soil nitrate number and calculate how much nitrogen I'm going to get in an acre foot of soil. It's basically, if everybody's seen the regional water quality control board's nitrogen calculators, this is better than that one. But it just gives you a target. So based on all of our, say, our water sample and our soil sample, it basically, and estimating that, I estimated high that we're 3 acre feet of water. That's actually a huge amount. Usually we do about an acre foot, a foot of water, sometimes less. But it just to get us a number here, it gave us a credit of basically 6 units of N per acre foot of soil. I usually work with an acre to 2 acre feet of soil in my mind when I'm thinking about fertilizer inputs for grapes. And then we can plug in our fertilizer input. So I'm calculating 12 pounds of soil applied N and 4 pounds of foliar applied N, to give us a total of 16 pounds, 16 units. And then I do use a multiplier for nutrient uptake efficiency. Typically, because no soil applied fertilizer is 100% effective, I typically use between 60 and 70%. Multiplier, it's kind of a guess. I usually adjust it based on what I see in the field, but you have to have a multiplier there because there's really nothing that is 100% uptake. Some foliar nitrogen sources can be close, but for soil applied, not so much. I'm running out of time. So moving along, our budget is going to be 16 units of N, 8 units of phosphorus, and 48 units of potassium per acre. If I was building a post-harvest soil building program, I would include, and this is a multi-year program because if you ran the numbers, it would be prohibitively expensive, but building soil is a long-term program. 300 units of sulfur, soil applied soil sulfur, 300 units of potassium, 300 pounds of potassium, and 100 pounds of 1152 in a band. Incorporate that over about 3 years, and we can really start to see some movement within the root zone. You're not going to change the whole acre, but we really want to affect the root zone. So I've built that. We want to understand our uptake curve. This is a general kind of curve for wine grapes and nitrogen uptake. So you can see from bud break to flowering, there's really not a lot of nitrogen uptake because the vines aren't really photosynthesizing. There's not a lot of evapotranspiration because there's not enough leaves. But you can see as we have after flowering and then into fruit set, that demand really peaks. And so we have actually these 2 peaks, but both at fruit set and then at right before veraison. And so those are the times where we really want to think about applying our nitrogen fertilizer. So I like to get my nitrogen in very early, typically pre-bloom to mostly pre-bloom, because I want to have my nitrogen levels up here before the requirement is, not at the requirement, because again, it's not going to get into the plant immediately. So we got to take that into consideration. There are curves for phosphate and potassium as well. So this is an example of a fertilizer budget where I have my units of N per acre here in this column, my units of P in this column, and my units of K in this column. And so I've said, okay, I want to get 8 units at this timing, at that 6-inch growth timing. I want to get 5 units of P at that timing and 3 units of K. And so this is the blend that came out of that. I really targeted my fertilizer around units per acre, not in a blend. And so you can see at this post-bloom set, a little bit of nitrogen, potassium, pre-bunch closure, so right before veraison. Again, that's where we want to target a lot of our potassium. And then obviously post-harvest, which I consider post-harvest a very important application in wine grapes. It's typically the first application for the next year because you're setting the amount, you're allowing the vine to take up and store especially nitrogen and potassium that it's going to use at bud break through about 6 inches of growth. All right, so then we want to select our fertilizers. We have a lot of choices. I could probably talk for an hour about different fertilizer sources. But what's really important is understanding that, when we're dealing with liquids, always know basically how many units of N are going to be in a gallon, or units of P or units of K in a gallon, and understanding bulk density in fertilizers. All fertilizers have different bulk densities. So a gallon of AN20 does not have as much fertilizer or nitrogen as a gallon of UAN32. And unfortunately, those are things that people don't think about. But it's important to think about, so keep that in mind. We want a jar test. This is a great one, Fluid Fertilizer Institute. This is like old school right here. I had to pull this and photocopy this out of a magazine or something. But this just talks about compatibility. And really, when you build a blend, now what? Well, we really want to make sure, we don't have any incompatibilities, because at the end of the day, we want to get the fertilizer into the plant. And we can cause issues just by blending fertilizers together. So it's very important to jar test. We want to, obviously when we're building a jar test, we want to maintain the proportions of the blend. I recommend storing those for 2 to 5 days. Can't tell you how many times I've built blends and delivered them, and then they've sat there for 2 weeks and it froze one night. And then, somebody calls me and says, why is this salted out? Well, it was really meant to be applied within the next couple of days. So anyways, keep a record of those, keep your jar test, take photographs and everything. It's just important. And that way, what blends are compatible if you're going to build that blend again down the road. All right, finally, you're going to complete your prescriptive program. So again, this is kind of an expansion on what what we're looking for. What we have here is we have the time. So here's our timing. Here is our products. Here is our quantity. And then this summarizes basically what we're applying over the course of the season. So this would be an example of a soil applied program. Foliars we can do as well. I didn't talk about micronutrients again, just because I didn't have much time. But I like to apply most micronutrients other than iron foliarly in general, especially in that soil that we were looking at. Iron, if you use a good chelated iron source, even in high lime soils, you can, the vines take up iron, I think, in a much more efficient way through their roots than foliarly. That's just my opinion. And then finally, we want to monitor that nutrition throughout the season. So what does that mean? That means taking tissue samples. You got to check your work. I like to take a minimum of 2 samples over the course of the season. I like to take a pre-bloom sample. That tells me, again, where I am with nitrogen and potassium and our micronutrients, calcium. And then I like to take a post-bloom, kind of a pre-veraison sample. That tells me where I'm at with potassium, especially if I'm kind of shooting in the right direction. I've got the right amount of potassium in. I won't get into sampling sources and everything like that. I'll just leave that with wine grapes. I like to take whole leaves. That's blade plus petiole, and I'll just leave it at that. So remember, at the end of the day, a fertilizer plan is just that. It's a plan. They can and they will change during the season. So be flexible, be willing to change, to be able to really zero in on what you're looking to accomplish. And like I said, you can and should modify your plans as you monitor that crop throughout the season through timely tissue sampling, and then also correlate your tissue samples with visual, with visual walking through the field and scouting, because what might show up as deficient on a tissue sample might not really be deficient in the field. So that's something to know. And then finally, be guided by the 4 R's. The right product, the right time, the right placement at the right rate. So with that, my email's on there. Sorry, I went a little bit over, but like I said, I'm trying to go through this really quickly, but I can talk for days about this. But if anybody had any questions or follow-up, you can certainly email me. I'm certainly happy to answer any email questions. I believe Miranda also has she might have my personal email as well, which is winepca@gmail.com. You can certainly do that. And so there is a couple questions. let's see. How might a table grape program differ? Typically units, you're removing a lot more with table grapes. Also, your targets are a little bit different because you're also farming for quality or for a visual grape bunch. So your nitrogen inputs as well as your calcium and potassium inputs are probably going to be definitely greater in table grapes just because your yield, you're moving so much more. Daniel, I said I do take leaf tissues. I don't take petioles. I am again, I'm a Washington. I went to Cal Poly San Luis Obispo, but I'm a disciple of Washington State viticulturist. Joan Davenport from Washington State, phenomenal, amazing viticulturist. And she, her studies up there in Cabernet and things like that have really shown that whole leaf, so blade plus petiole, gives us a little bit more of a consistent number. And honestly, I mean, I guess talking about sampling, if you've petiole sampled your entire life and that's what you base your samples on, then stick with petioles, because you've normalized those numbers to what you see in the field. So I would, and stick with the same labs too. And so that's, anyway, we could talk about tissues all day. I will leave it at that.
Yes, and keep in mind too, you can type questions into the chat, and Paul, I think you'll be able to answer them in the Q&A section as well.
Yeah, I can type them in while I'm doing it.
Yeah.
So I will.
Thank you.
I will stop sharing now. Let's see. Stop sharing.
That was awesome. I think I'm going to adopt your mantra for sure. So and next up, we have Dr. Danny Klitich. He's the Director of Agronomy at Mission Produce, and he earned his master's and PhD from the University of California, Davis, where he studied the influence of fertility programs on pest populations. His professional background in practical farming and the ag retail wholesale industry brings a unique approach to fertility. So Danny, thank you so much for joining us, and take it away.
All right, there we go. I had to remember to unmute myself. All right, well, pleasure to be here with you guys. I'm excited to talk about avocado fertility. Actually, a quick rundown of the plan here. We're going to talk about the 4 R's once again. Thank you, Paul, for doing a brief run through on those. We're going to dive in a little bit more specifically on avocados. We'll talk a little bit about utilizing analytical testing, which has been great, that we've had several overviews of that already, and kind of where I fit those in when we're looking at avocados. And then we're going to go through the primary nutrients that we look at within avocados when we're building out a fertility program. My legal department wants me to make sure I put in a legal disclaimer here. So there it is, in case you're worried that this is for information and educational purposes, and I'm not guaranteeing anything. So there you go. So as you're all aware, being within the agricultural industry, there's a lot of fertility products on the market. So I talked to Agri-X down in Oxnard. They have 486 fertility SKUs in their system, right? So there's a lot of choices on the market. And then we take that incredibly complex fertility market and we stack it on top of a crop phenology. And this is avocados. We put together this table to kind of help highlight how complicated this evergreen subtropical tree is that can take 2 years to produce a crop from when we first start developing budwood to when we pick that avocado off the tree and send it into the packing house. And at that same time, we have another crop going. So we have an alternate bearing issue in avocados, generally because they're on the tree at the same time. So, but you can really see at certain times of the year, a lot of things are happening. And at other times of the year, very specific things are happening. Like in summer, we're really just sizing fruit, whereas in spring, we're having bud development and we're having a lot of blooming. We're having periodic root flushes throughout the year. And of course, we're having overlapping things happening, like we have our on-crop fruit cycle sizing while we have our off-crop budwood development and bloom and so on and so forth. So a complicated, overlapping, very busy tree with a lot going on. So the goals of fertilization, the way that I have approached it, is really we're fertilizing to drive yield. We're also doing this, providing supplemental nutrition during periods of extremely high demand, and properly timing our fertilizer applications is really critical. I like this quote from Dr. Lovett from UCR. The goal is to increase fruit set, size, fruit quality, and grower profits, even when the tree is not deficient by standard tissue analysis. So we're really pushing that tree to achieve a yield goal, but we're doing that in a strategic way. So when we're doing fertility planning, we still need to be responsible. So I think that last quote, some people could take that as, well, that's way too much fertilizer, but we really need to be strategic in the way that we apply our fertilizer. And we still need to stick with those 4 R's to make sure that we maximize our return on investment for products that are applied: right time, right form, right source, right place, right rate, right place, right? So that right time, I highlighted that we have these changing tree needs throughout the season, and making sure that we target those needs is incredibly important with the correct nutrients that tree needs during those periods. Of course, we need to have that right form and right source, which comes down to the solubility and the anion-cation ratios, the cost per unit, the cost per acre, the cost per application, the ease of that application, compatibility with the system that grower happens to have, and of course the bioavailability of that nutrient, making sure it actually shows up when we need it within that timing. The right rate is incredibly essential, and we'll talk about that here a lot with this right place. We need to fertilize for the crop that we have in the stage of the tree. Like I said, we have avocados that alternate bear quite a bit. This is a picture of a lambhash tree that's absolutely loaded. This tree this section of the orchard is about a 5-acre section, ended up producing this year almost 50,000 pounds per acre with this crop load. The state average is 6,000 pounds per acre. So there are some unique situations where more fertilizer is better and needed because the trees just happen to need it, but we still need to be smart in the way we put it out. So when you're dealing with a crop that we can have these insane shifts in crop load, we really need to make sure we're not just cookie cuttering our fertility programs year over year and then wondering why are all my fruit really small and why are my fruit really big some years and why are my pounds all over the place. So we really need to look at that rate, and we need to be intelligent and intentional in the way that we assign that rate and when we apply it. And the last one is the right place. So there's many different ways that people interpret the right place, but I have 2 specific ones I want to highlight here. So this is what level in the soil does the fertility need to be at? Avocados are a subtropical tree, rainforest tree. They have a very shallow root system and feeder roots. So that's a picture of my boot there next to the roots. I kicked back the leaves a little bit. You can see here in this other picture, the roots are just sticking up, and they're literally 8 to 12 inches below the top of the ground, not in the soil, just wherever the leaf duft starts. 8 to 12 inches down from there is where these roots are. So as you can imagine, we're managing a very specific zone within the superficial layer of the soil, as well as the actual mineral layers of the soil. And we're really looking at really just a top layer. So we need to manage the water in that zone to maintain a good moisture level, but we also need to make sure our nutrients stay in that level through targeting our fertility applications. Avocados have these very fibrous roots, you can see in there, and they don't have root hairs, so they're incredibly terrible at pulling nutrients out of the soil. They have great symbiotic relationships with soil fungi to help with that lack of ability to really extract nutrients out of soil. However, we need to make sure that we have a good condition for that symbiosis to happen. So we're going to try and target our fertility applications to keep the maximum amount of our fertility in that top couple inches of soil and try not to leach it through. The other thing we want to make sure is that we don't put out too much at one time. So I love this picture. Here's somebody that said, go throw the granular fertilizer out, didn't train their field staff on how to do that, and lost pretty much several years of production because they defoliated their entire trees because they oversalted their orchard with, I think this was water-soluble triple 20. So it was right there, right now, right? So there was a lot of decisions that were made wrong that got them to the place where this went wrong, which obviously they were not talking to a qualified person to make this recommendation. And this is a great example of the moron effect coming into full exposure, where moron did not work out. We did not put more on and get more crop. We put more on and looked like a moron. So So let's make sure that we keep our right place in terms of that distribution of the fertility around the root zone also. So all avocados are irrigated in California, otherwise they die. Therefore, everyone has a sprinkler system or a dripper system, and all the roots are now located in that wetting pattern. Therefore, applying fertility within that wetting pattern is the best we can do. I understand some people still like to put out dry because they feel like they get something out of it. I don't quite understand how that works because the roots are where the water is. Therefore, why don't we put the fertilizer through the water? So I always push people, if they are using dry, avoid this situation from happening and make sure that we target that fertility to actually end up in the wetting pattern of the sprinklers through utilizing liquid fertilizer. So that's the right place. So we're going to try and put the fertilizer where the water is, and we're also going to put that water where the roots are. And hopefully that water has the fertilizer in it. So that's the right place that we're going to try and target. Okay. Analytical testing. Paul mentioned a great list of things we need before we go in to look at how we're going to put together a fertility program. And analytical testing is incredibly important to make sure we understand where we're coming from, have a goal of where we're going, and understand what's going on within the orchard. I totally agree with Paul's statement of a soil test in the last couple of years would be great. I'll even go back as far as 5 if they're not doing anything nothing has really changed within the orchard in terms of their general practices. We're really looking at soils, the way I approach is we're looking for general possible deficiencies. We're looking at anything that might impinge our water movement, high magnesium, high sodium, chloride buildup, sulfate buildup, things like that. Looking at our overall salt number, preferably we're going to look at a soil sample if we have the dream situation, one from the beginning of the season, one from the end of the season, so we could see what changed over time with that management practice. And I always like to look at what the organic matter looks like. As you can see earlier from that picture, of my boot in the root area, it's not uncommon to see avocado soil samples come back with 5, 6, 7% organic matter, even though the parent material is going to be at like 1, 1.5, 2%, because it really self mulches, and we really want to build that mulch layer and have that high organic matter, and they really thrive with that high organic matter. So if I see an organic matter come back on an avocado orchard that's been established for a while, that's in that 1 to 2 range, there's some questions there about some soil management practices that need to be addressed. We're going to look at water. I think we've talked a lot about water. EC avocados fall into that super salt sensitive category, even more so than cabbage. I think was the loser on that list. I think avocados would be right there along with it. We really like to see an EC under 1. We can take waters that have higher ECs, but we need to really make sure that those avocado orchards are then planted on very well drained soils. Nitrogen content that water is a big deal. Avocados are using 3 to 4 acre feet a year is our general water usage for avocados. So we want to make sure that we take that calculation into account when we're looking at how much nitrate we're putting out through our water. We're on the Central Coast. We have some waters that across the whole year, we might get 110 pounds of nitrogen just in that 3 acre feet very easily. So we want to make sure that we take that into account. We're looking at our nitrogen content and make sure that if we are high on nitrogen, we're backloading that with potassium and calcium and other nutrients to try and overcome that excessive nitrogen in periods where we don't necessarily need it. SAR is important. Calcium magnesium ratio is important. All these things are great. So we're going to skip through that. The next one is obviously we'd love to see a tissue test. Avocados are notorious for having nitrogen and potassium are low, and zinc also being low, especially in Ventura and San Luis Obispo counties. We see slightly different changes down when we get into San Diego, where we'll see higher phosphorus and higher zinc numbers, but we'll see some nitrogen, some other issues that kind of twist things around. So it's always good to have a leaf analysis. I did want to highlight this though, and I think Paul once again highlighted this as well. We still need to go look at the orchard. I was in an orchard last week, and this was their tissue analysis. Beautiful tissue analysis. Everything looks ample. Everything's really good. This was their trees. The trees looks not good, and they realized that, and they were confused, saying, "Hey, look, this analytical test says things are awesome. I know how things aren't awesome. So what did I miss here?" So, and that's where we kind of got to talking more about other management practices besides fertility. Today, this talk is about fertility, but it's really a holistic approach, especially we're dealing with sometimes amateur farmers or people that have just done it the way grandpa does it, and things have changed. So we really need to look at the entire management practice, from irrigation, how they irrigate, when they irrigate, and all the way through to pruning and fertility and pest control. So, but I always like to highlight tissue samples are only part of the fertility plan. One other thing on tissue samples is avocado tissue samples have had an update recently, which is I think kind of weird within tissue sampling. Most of those numbers have been around for quite a long time, but the Avocado Commission did a big study across over a decade's worth of data that they analyzed with UC Riverside and Carol Lovett, and they went through, and also some other people at Riverside, I can't remember their names, and they put together new brackets that they used across about 600 different samples. They compared to yield data, and so they changed around some brackets that were not what was standard. Some things went up significantly, some things kind of shifted around, and the top ends came down. They are different. Most orchards are still going to fall within mostly good numbers, but it is important when you get back a tissue result to just verify what brackets we're actually comparing to. Because it's something that usually we just take for granted the lab picked the right ones, and a lot of the labs haven't shifted yet onto this newer standard, which honestly, a lot of the times, like for example, calcium went up by about 0.5% over the old standard, which is a big shift. So a lot of the old samples that say calcium are fine will now say that calcium is short, which is something that's never been on anyone's radar. Zinc went up even higher than it was before. So that was something that a lot of people were minimally deficient on before, are now showing really high deficiencies on. So these things, and boron went up as well. So there's a lot of these things that shifted around that really need to be kind of, I think it really highlights some of the intricacies that we've been missing within avocado fertility due to kind of the simplistic approach we've used historically in avocados. Okay, so plant nutrition, how are we doing on time? 10 minutes, awesome. Okay, you guys all know this. There's a bunch of different types of nutrients. We call them macros and micros. They're anions and cations and all kinds of fun stuff. I'm gonna run through the top couple here that we concentrate on and just kind of what we associate that with, and then we'll talk about where we're gonna stick it in a program to accomplish that goal. So nitrogen does it, and before I go here, all of these nutrients do a lot of different things. However, pegging them or distilling them down to one specific or a couple specific roles within that crop phenology where a deficiency will really cause some problems, I think really helps when we are trying to rationalize to a grower or to ourselves or design a program. We can't be thinking, oh, nitrogen, it's a key component in DNA. When am I going to need to build DNA? No, that's a cool fact, but really it's, well, we need nitrogen to push vegetative growth and really for budwood development. So when are we pushing budwood development? Okay, that's our late fall. We need to have nitrogen present late fall to make sure that we push that budwood development. Same thing, we need to make sure we have vegetative growth to cover our fruit. So we're going to make sure we have that there in June. So we're going to push a big pop of nitrogen preceding June or in June to build that vegetative flush we need to cover our fruit. Potassium similarly is really important in fruit sizing. Has a whole bunch of different roles, heat tolerance and all these other places. But that fruit, like I said earlier, if we have a crop on there, call it a 10,000 pound crop, which would be a decent year for many people. There's a lot of potassium being sucked out of that soil, out of the water, and being put into the fruit. In this particular study that they did, this was done mostly down in a ranch where they had a little bit of sizing that was over the summer, but the majority of their sizing was early spring. So that size development was really correlated to potassium accumulation within that fruit. You'll see this is different than other nutrients. So when the fruit is sizing, we really need to have potassium present within those systems. And in some of these systems, we have fairly cold soils in March through June in some of these areas. So we need to have potassium in a soluble form in that root zone. Luckily, we have a lot of organic matter there and a lot of other things that are going to help with our potassium cycling and minimize mineralization of our potassium, but we need to have it there. Otherwise, we're going to reduce our sizing potential of our fruit. Calcium is really important for fruit quality as well as tree resilience. We've also found that more calcium equals less fruit drop. Fruit drop's a huge issue in avocados. It's really cell wall strength component. It's huge. This is interesting. So this is the same study they looked at potassium accumulation within the fruit. Calcium is really only accumulated within the first couple months after pollination. So we really need to have that calcium there early in the fruit development. And this is true across most fruiting crops that we grow, that calcium is really accumulated within those cell walls in the early fruit development. And then you think of it, we're just blowing up those cell balloons later. That cell wall is already there, and we're blowing up the balloons of those cells with our potassium and our zinc and our other things later on down in the development cycle. Okay, so that's fruit calcium content. Zinc. So zinc is a structural component in tons of enzymes. Avocados have a very notable zinc deficiency where they get these little round fruit that look like golf balls. They don't get a whole lot bigger than golf balls even. You might see it as big as a racquetball, but they'll be perfectly round. You can see here, this was a nice orchard example of having a zinc deficiency. We don't see this a lot, but we see it a lot in organic production where manure is used a lot or other high phosphate containing fertilizers. Because phosphate ties up with zinc. We're also not generally acidifying in those situations because it's too expensive in organic to acidify in most cases, at least not acidifying in the water. And that will come around to having higher likelihood or occurrence of zinc deficiency within those organics. We'll also see it a lot in really heavy set years where the tree just can't keep up with zinc demand. And so we end up with a zinc deficiency with a bunch of golf balls on the tree. It's really quite impressive when you walk into an orchard. You're like, oh, look at that. You have a zinc deficiency. All you have up there are golf balls. And they go, I've never put on any zinc. You're like, oh, there we go. That's great. Next year's going to be a good year. So boron is another one of those. On the coast, we have a lot of areas that have a lot of boron in their water. However, boron is needed by the crop in springtime for pollination and bloom development. And if it does rain, which it does sometimes here, I'm told, boron leaches out of the system. It's a fairly leachable product, a fairly leachable ion. It's also less available in high pH soils. So you can end up actually having a decent amount of boron in the system, but in cold springtime soils, you have very low availability. It also doesn't help that a lot of people that grow avocados also grow lemons, and lemons are extremely boron sensitive. So if you have too much boron in a lemon orchard, it's a very, very bad problem. They get very ugly. If you have too much boron in an avocado orchard, it can be a problem, but you're talking a massive amount of boron late season causing a big issue. And even in those orchards, early season boron might be short because their water quality is better early and their boron availability is just not there when it's actually needed. So there's some research that shows that boron is semi-mobile within avocados, so you could have some stored boron within the tissue that might help with pollination, and it probably does to some extent. However, some boron early makes a huge difference. And the last one's carbon, that soil health component, making sure that we keep that soil microbiology going as hard as it can and being as active as it can, really makes a big difference on nutrient availability and overall root system health of an avocado orchard. We're going to skip the long-winded quick notes and we're going to go to the quick notes here. So really our quick notes here, we're fertilizing to push yield. We really want to do tissue, soils, and water analysis to make sure we have, so that it's good to know what you're dealing with. Tissue reports are a report card on how the management program worked, but it's only part of the overall management plan. So we need to make sure we also look at fruit load, tree vigor, fruit size, yield, et cetera, when we're considering an overall soil health program. Nitrogen for growth, potassium for size, calcium for quality and less drop, zinc for size, boron for set, carbon for soil health. Okay, I am pretty much out of time. I'm going to put these slides up here. So if you're watching this on the recorded one, you can pause it and look at it. But this is generally what's happening in like Ventura through San Luis Obispo. This is pretty much the middle of the state. We're calling it for avocados, we'll call it the Ventura region. If you're down in San Diego, you're going to shift this a couple months earlier. If you're up in San Luis Obispo, you're going to shift this a couple months later. But this is pretty much what's happening within the avocados and then what nutrients are needed. So we'll just pick April, for example, because there's a lot going on in April. We have bloom and set in April. The sizing, if it's warmed up a little bit, we're going to start sizing some fruit. And we're also picking. So we're going to be looking at a little bit of nitrogen, a decent amount of potassium, a good shot of boron, and a good shot of calcium. That's going to be our concentrations, or where I've approached in April. Let's oppose that to June. June, we're not really worried about size. We're not really worried about pollination anymore. Bloom is pretty much done. Boron, we don't need boron anymore. So boron has been pulled out of the program. Here is the mission generic fertility program this is pretty much our base program for all our orchards. We have about 400 acres of orchards of avocados. That this is kind of the standard program we start with. Obviously, every orchard gets tweaked a little bit, but year over year, this is what we're starting with, and then we're figuring out more micros, less micros, more of this, a little bit of that. How our nitrogen look, a little bit here, a little bit there. Oh, it's warmer in November, we'll still be fertilizing then. Oh, it rained a lot in January, or it was beautiful in February. You know, we're going to change some things, but this is kind of the overall generic program of where we're going to start. Okay. That's all I got. Thank you. Thank you for watching. And if you have any questions, I'd be happy to take those now.
Thank you, Danny. That was awesome. Good job doing a quick presentation there and packing it full with information.
Yeah. So
any questions coming up?
I got one question here from Daniel Robledo asking what causes black veins inside the avocados. So that is generally a storage issue that happens post-harvest, or it can be varietal depending on what variety you are, but I'm going to assume that this is in regards to a Hass variety that you bought in the grocery store that you'll get black veins sometimes, and that's generally a post-harvest handling problem where it was picked and it wasn't put into cooling fast enough, and that can develop black veins fairly quickly. Because it's kind of weird, we don't really think of like the vascularization of avocado flesh, I guess, if you want, you know, the inside of the avocado, but there's vascularization up there, and those veins are becoming anoxic and causing problems. So you can also get some secondary infection that comes in through the stem. So the button can fall off sometimes, called the button, the little stem that's left on there, and you can get some fungal infections that can come in and and cause black veins in some cases there as well. So that's that one. Anyone else? All right, thank you, everybody.
Thank you. So now I think we're going to put the QR code on the screen so everybody can get their CEUs. So you can scan that directly from your CCA app, mobile app. And also remember, this is a series of 3. So you can come and join us Friday, December 2nd from 1 to 3 and Friday, December 16th. And the agendas are posted at the website where you can register for those events. It's the same page as where you registered for today's webinar. So everybody, thank you so much for joining. And I'll give you some more time to scan that QR code. And then I think that we're also going to post the speaker's contact information if you would like to email them any questions.
Thank you, Eryn. Good job.
Oh, thank you. Great presentations. I took notes, learned a lot. Thank you so much.
Everyone did great.
Yeah.
All right. Have a good weekend, everybody. Happy Thanksgiving.
Have a good weekend. Happy Thanksgiving.
Okay, I'm gonna go ahead and just leave this on the screen for people to scan for the next little bit, and then, you know, around like in about 5 minutes, I'll probably just shut the whole webinar off. So people are free to go as needed, and thank you everyone for your time and efforts.
Yes, thank you.
Thank you, Miranda, for keeping us going.
Yep.
That was a great meeting.
Yeah.
Right, and you don't have to do it anymore, Eryn. You did your deal.
All done with the MC. I'll be speaking during Carl's webinar though, so you gave me some really good ideas for what to include in that, because it's salinity and irrigation water. You covered it pretty much, so thank you.
You got it. Well, hopefully I didn't ruin it for you.
Not at all, no. Yeah.
All right. Well, we'll see you on the next one, and then probably at our quarterly meeting too.
Yes, I'll see you both there. Thank you.
All right. Have a good weekend. Bye-bye.
You too. Bye.